I have this mic today, not the clip-on one. That one works worse. This one's better. Does everybody know how to find the review to practice? It's on, if you Google UCF Study Union WordPress, it comes up. Find my name, find Chem 1A, and it's Chapter 6. Those who aren't in Dr. Hernandez's class in here, I'm just letting you know that he's only testing on Chapter 6 for their final, so that's what I'm going to be going over mostly. It's Chapter 6. What I'm going to do is I'm going to go over this for about an hour and 20 minutes. That's what I'm going to shoot for. And then the last 40 minutes or so is just going to be questions. Any questions you've had from the whole semester, different things, you know, it'll be that. It'll probably run closer to an hour and 30, but I'm shooting for that. All right? Any questions? Comments, concerns? Oh, this is my second review for today, so I am pretty tired. So if I make a mistake, please correct me. If you can't see something, let me know, because I've done that like 5 times at least already, where it's like this and you can't see it. So, all right. All right, I'm going to start. So the way the review is organized is it starts from the beginning of the chapter, going to the end of the chapter. We're going to start easy with internal energy stuff and finally end up with H of formation, H of reaction. Okay? All right, let's get started. Get adjusted here. All right. Let me use this pen. All right, so the first question is the internal energy of a system is increased by 982 joules when it absorbs 492 joules of heat. Was the work done by or on the system? How much work was done? What is delta V if the pressure is constant at 1 atm? So we have the internal energy. What's the internal energy variable? Delta E. Increased by 982 joules. Okay? So we know the formula corresponds to delta E. It's delta E equals Q plus W. Okay? So we know it absorbed 492 joules of heat. What does absorb mean for the sign? Awesome. It's a positive. So it increased by 492 joules. Okay. And now we can find our work. Well, delta E is 982, so 982 we find our work to be 490 joules. Okay? So then, was work done on or done by the system? Okay, so was work done on the system? Yeah, it's a positive. So we did work to it, we're adding energy to it. It's not done by it because that would be a negative. So work is 490 joules. And then we can figure out if the pressure is constant at 1 atm, what is the delta V? Okay, so what's our formula for work? Work equals negative P delta V. Okay, negative P delta V. We have our work is set equal to 490 joules, which equals negative P. Can I leave pressure in atmospheres, or what do I have to change it to? So I have to change it to 1 atm equals 101.3 joules per liter. Okay? Good with that? Joules per liter, so we get 101.3 joules per liter times delta V. So we have delta V in liters. Okay, so we can go ahead and solve. 490 divided by minus 101.3. We get negative, I don't know if you guys can see that, negative 4.83 delta V equals negative 4.837 liters. Okay? Sig figs, we can keep it in 3 if we want, but you get the main concept. Delta V equals negative 4.84 liters. Any questions on this one? Yes, no, maybe? All right, let's keep moving. All right. A gas in a cylinder was placed in a heater, gained 550 kilojoules of heat. You can't see that? You see, that's what you guys got to tell me. If you can't see it, you're going to let me know. 550 kilojoules of heat. The cylinder increased in volume from 345 milliliters to 1846 milliliters against atmospheric pressure of 750 torr. During the process, what is the change in internal energy of the gas? Oh, my fault. I moved that out of the way. Man, I'm off today. Thank you. I appreciate it. All right. So, what is the change in internal energy? So, internal energy, what variable you think? Delta E, thank you, equals Q plus W. All right. So, we had a heater and gained 550 kilojoules. Or 1550 kilojoules. There we go. 5500 kilojoules. Okay? Plus W. So we have something that expanded against atmospheric pressure, but we're giving it in torr. How much to convert torr to atmospheres? What's our conversion factor? 760 torr is 1 atm. So 750 divided by 760 equals 0.9868 atmospheres. And remember, so we're using plus negative P times delta V. Okay? So we have to, what do we have to convert this to? Joules per liter. So we're in atmospheres. We're going to go ahead and we're going to multiply this by joules per, by our 101.3. So we get, I'll put it here, times 101.3 joules per liter. Or joules per atmospheric, to be exact, times 101.3. We're going to get 99.967 joules per liter. Okay? So now we're going to use negative P delta V. Negative P. 99.967 joules per liter. There's delta V. We have to change this to liters because we need liters to cancel out. So we have, how do we find our delta V? VF minus VI, put that here. Volume final minus volume initial. What's my final volume? 1.846 liters minus 0.345 liters. Okay, and let's go ahead and plug this in the calculator. Big calculator today. All right, so All right, we get a negative 150.05, and that's in joules. 0.05 joules. Can I subtract kilojoules from joules? No, so I'm just going to change this to kilojoules because it's fairly simple to do. You just move the decimal point 3 places over. Now you're in kilojoules. 5500 kilojoules. We can find our internal energy. So this is plus 50. We get 5499.85 kilojoules. We can find our internal energy change that way. Okay? Questions? Okay. Let's keep. Yeah, question. I can't see past the podium. So that's the conversion factor between torr and atmospheres. It's just a conversion factor. No. 1 atmosphere, yeah. Okay? Yes. I don't even know if did he do this one in the, did he use torr in the chapter? Then chances are, if he doesn't touch it in chapter, if he hasn't put something in the PowerPoint, has he put it on the test? I just put it as insurance just in case. You know, there's conversion factors between millimeters of mercury, which is the same as torr, which is, the same conversion factor, which is still 760. Okay, so it's good to know, especially if you're engineering or something else like that. It's definitely good to know. It's good to know if you're going to go in future in chemistry. Okay? Questions? I got some confused looks over there. Can I move on? We got a lot to get to. Yeah. Move on, move on, move on. Again, I'm going to post this. I'm going to post the answer key. So after I'm done with it here, I'll post it tonight. Yes? Right here. I multiplied my atmospheres by my conversion factor that you do have to know, which is 101.3 joules per liter. And then you get 99.7. Because remember, the conversion factor is joules per atmospheric liter. And we're multiplying out atmospheres. See here, joules per atmospheric liter. You're multiplying out atmospheres, and you're left in joules per liter. Okay? Any other questions? I know this one's a little more involved than a standard, delta E problem, but I like you to be over-prepared. All right, let's keep going. Okay. So it says the change in internal energy from the combustion of 1.00 moles of CH4 gas in a cylinder according to the reaction CH4 gaseous plus 2 O2 gaseous forms. It's supposed to be an arrow there. I don't know what happened here. Forms CO2 gaseous plus 2 H2O gaseous is negative 942 kilojoules. If the piston connected to a cylinder performs 492 kilojoules of expansion work due to the combustion, how much heat is lost from the system? What is this system in this situation? All right, let's go over this. So we have methane burning. We have a combustion of 1 mole of methane burning according to the reaction. And we have negative 892.4 kilojoules. Okay, and we know that we have a work of negative 492 kilojoules of expansion. How much heat, or how much energy is lost due to heat? Okay, so we have a delta E equals a Q plus W. We have an energy, coming from this reaction, we have heat and work. So we know that 892.4 it gives off, so it's a Q plus kilojoules, okay? So we're trying to find our Q here. So we have 892.4. There should be a negative, yeah. That's a negative. 492. I'll do it this way. 492. Okay, so our Q is negative 400.4. So this is our, and it's kilojoules. So this is our heat lost in the system. Okay? Because if we know that the reaction puts out, we're burning 1 mole of methane, so this reaction has 1 mole of methane, puts out that much energy, okay? And we know energy is broken up for our purposes into heat plus work, okay? So we have a work value, so we just subtract it out, or add it out in this place, in this case, and we find our Q value, okay? Questions? Can I move on? Yes. That's a great question. So if this said I had 1/2 mole of methane, what would I have to do to this value? I'd have to cut it in half, because based on this reaction, it's given that there's 1 mole of methane in this reaction. Okay, there's not a 1/2 here. If I said I had 2 moles of methane, then it'd double the reaction. So I would get about double the energy. Okay? Can I turn? Yes. So are you asking why is the heat negative here? It's a good question. So when we're doing work, am I doing energy on something, or is it giving me energy? So when I push my phone across the table, am I doing work on the phone, or is the phone doing work on me? So does that mean I'm at a lower energy state, or is the phone at a lower energy state? So I use the energy. So if you think about it, when you go running, you come back and you're exhausted, okay? You did work, so you're exhausted. You're at a lower energy state. You need to get more energy, okay? It's the same thing with this. It's doing work, so it's doing work to expand the cylinder and the piston, so it's going to be a negative because it's at a lower energy state once it's done, okay? The reaction is, can you relight that methane once you already burnt it? It's like the gas in your car. Your car doesn't fill up the gas tank itself. You have to fill it up for it to go. Okay? All right, let's keep going. All right. All right, so this one's how much energy is needed to change the temperature of 50 grams of water by 15 degrees Celsius. Okay, so we know we have 50 grams of water, which is my M. We have a delta T, change in temperature. So what formula are we going to use? Equals MC delta T. Awesome. So we have a mass, we have a delta T. Do we know the specific heat of water? It's 4.184 joules per degree, or gram times degree Celsius. Equals my CS. Okay? Specific heat. I'll put an S here. All right, so I'm going to go ahead and plug in my values. I have an M, which is 50 grams. I have a CS, which is 4.184 joules per gram times degrees Celsius. And I have a delta T, which is 15.0 degrees Celsius. Okay, so let's make sure our units cancel and we're left in a unit of energy. So grams cancel with grams. Degrees Celsius cancel with degrees Celsius. And we're left in what? Joules. Cool. Then my calculator, 50 times 4.184 times 15. I get my amount of energy required to change 15 grams of water, or 50 grams of water, 15 degrees Celsius. Yes. So he's going to provide you with specific heats. However, I always suggest you know the one for water. And we'll illustrate that now. What if I wanted this joules number in calories? Okay, I want to convert joules to calories. Little calories for now. Okay, what's the conversion factor for joules to calories? There are how many joules in 1 calorie? 4.184 joules per 1 calorie. Okay? So you killed 2 birds with 1 stone, knowing the specific heat of water and knowing the conversion to calories. So I could divide that by 4.18 joules, 184, and you get calories. Okay? Questions? Any more questions? Okay. Let's keep going. How many grams of water can be heated from 20 degrees Celsius to 75 degrees Celsius using that amount of energy? Okay? So, what am I looking for? Mass. Awesome. We're looking for M. We have a delta T. And we have a Q, amount of energy and heat. Okay? And what's our CS for water? 184 joules per gram times degrees Celsius. So what formula am I using? Awesome. We're going to use MCAT. So Q equals MC delta T. All right. So my Q for water is 125.00.0 joules equals my M times my CS, 4.184 joules per gram times degrees Celsius, times my delta T, which is my TF, 75 degrees Celsius, minus my TI, which is 20.0 degrees Celsius. Okay, and I'm going to go ahead and just solve for my mass. So I can do 75 minus 20. I get 55 times 4.184. Okay, I get 230. So I'm going to do 12500 divided by my answer, 2500, and I get my mass 54.331 grams. Questions? Fairly simple, right? It's routine. Once you know the formulas, you'll be good. All right, let's keep going. So again, more of the same. What is the final temperature after 840 joules is absorbed by 10 grams of water at 25 degrees Celsius. So we're looking for, so the way I structured this was I had you finding each different variable that could be asked. Okay? So we have 840 joules equals my mass. So this is Q, M. This is my T what? Ti, and we already have our CS, which is from every other problem we've done. So M grams, 0.184 joules per gram times degrees Celsius. And remember, the specific heat is specific to the element. So if you don't have water, it says 10 grams of iron. You go to the table that's going to be provided, or the thing that's going to be provided in the question, saying this is the specific heat of iron, copper, whatever. Okay? All right. So we have TF minus my TI, which is 25 degrees Celsius. Okay? And there we go. Let's go ahead and solve this. Okay, we get 20.076 equals TF minus TI, which is 25 degrees Celsius, plus 25, 45.07 degrees Celsius. Is going to be our TF. And again, you don't remember scientific calculators, not graphing calculators on your test. I'm using this because I need this for a different class I was studying for and can't find my scientific one. So there you go. All right? Any questions on this one? All right, let's keep moving. All right, a different one. The heat capacity of aluminum is given. How much energy is needed to raise the temperature of a 8.50 times 10 to the 2 gram block of aluminum from that to that? So this one's solving for Q. What formula are we going to use? MCAT Q equals MCS delta T. Okay. We get our M. What's my M? 8.5 times 10 to the 2, or 850. 850 grams times my CS, which is right here, 0.900 joules per gram times degrees Celsius, times my delta T, which is 94.6 degrees Celsius, minus 22.8 degrees Celsius. I'm going to plug that in my calculator. We get 54927 joules. Questions? Again, this is what I was saying before. You switch the C. There you go. The other type of question, I don't know if I put one in. Let me see. Is if you're given all the variables except for C, given your mass, your delta T, and your Q, and solving for C or CS, if you find your CS and it says, for example, what metal or what element is that, you match the CS up to the table you're going to be given, okay? So if I'm looking for this and I find my CS is 0.900 and I look in the table and it says copper is 0.385 and water is 4.18 and it says aluminum is 0.9, I could say, okay, I have a block of aluminum here, okay? Any questions on this page? I think it's pretty straightforward. All right, let's keep going. Speaking of, I think this is the same thing. I mean, not the same thing, but what I was saying. All right. Okay, let's do this coffee cup calorimetry problem. All right, so a piece of metal weighing 59.047 grams was heated to 100 degrees. So 59.04 grams, what variable is that? M. Heated to 100 degrees Celsius. This is going to be my Ti for the metal. Then put into 100 milliliters, which is going to be my M, of water, initially at 23.7. I'm not going to write Ti, but that's my Ti. The metal and the water were allowed to come to equilibrium temperature, can't speak, determined to be 27.8 degrees Celsius. Assuming no heat lost in the environment, calculate the specific heat of the metal. Okay. So I'm gonna draw it. It's hot water or hot metal? Hot metal. Okay. So we have a coffee cup. Something we become too familiar with during finals week. Coffee cup with cool water in it. Okay. The water is, let me see where the water is 23.7 degrees Celsius. Okay. Water is 23.7 degrees Celsius initially, and we have 100 milliliters of it. Okay. And we're putting a hot piece of metal with a mass of 59.047 grams and a temperature of 100 degrees Celsius into that water. Okay. So when it's all said and done, we get, put it here, that our metal in the water is at a temperature final of 20.8 degrees Celsius. Okay, so what does it mean to come to equilibrium? That's a question for you guys. Yes? Awesome. Same final temperature. So the water's temperature is the same temperature as the metal. So there's no heat being exchanged anymore. All right? So when I put this hot block in here, into the cold water, where's heat flowing from? Awesome. The block to the water. The block to the water. So this is going to be, so the water is going to have a positive or negative Q. Is it gaining heat or losing heat? So is it going to be positive or negative? So it's going to have a positive Q. What's the block going to have? Awesome. It's going to have a negative Q. Cool? So remember, we did the Q for the calorimeter equals the negative Q in the block, whatever. So the way I like to look at it is Q for the water plus the Q for the metal equals 0. Because no heat is lost. Is this amount of heat that's lost by the metal the same as the amount of heat gained by the water? So Q for the water plus Q for the metal, because one of these is going to be negative, and we already know that this one's going to be negative. It's going to equal 0. Okay? That's just the way I look at it. You can do the Q equals negative Q thing. Go for it. I do Q for the water plus Q for the metal equals 0. All right? Let's go to the problem now. So assume no heat is lost to the environment. Calculate the specific heat of the metal. So if we have Q for the water plus Q for the metal equals 0, What's Q equal to in formula? We have an M, we have a CS, and we have a delta T. So what is it? MCAT. So we know the Q. So we have MCAT for the water, and we have MCAT for the metal equals 0. Okay? Everybody following this far? Questions? All right, let's keep going. So MCAT plus MCAT equals 0, and we know that this is the water and this is the metal. All right, what's my mass of water? What? 100 what? Cool, but is milliliters a mass or a volume? This is a volume, right? So what do we got to know before we can figure out the mass? Awesome, the density. Remember, going back to chapter, I think it's 2. The density. Awesome, that's why I put that in here, because this is a common mistake, even though it doesn't matter in this one. But, so the density of water is 1, you can't see that, put it here. 1 gram per 1 milliliter. Okay? So how much does this weigh? 100 grams. Okay? 1 gram per milliliter is this is called a rho. This is the symbol that's pretty much used for density all the time. This is the density. Kind of looks like a weird P. All right. So we have 100 grams of water. So we can change that to grams. Since it's water. If this was 0.9 grams per 1 milliliter, that is different. But then not for water. If you had, I don't know, some other thing you're putting it in. Or we'll stick with water. So my M for water is 100 grams. What's my C for water? 4.184 joules per gram times degrees Celsius. What's my delta T for water? What's my TF? 27.8 degrees Celsius minus my TI, which is 23.7 degrees Celsius. That's a C. Okay. Plus, let's do my metal now. What's my mass of metal? 0.047, awesome, grams, times my C for the metal, which is what I'm looking for, right? So my C for metal times my delta T. What's my TF? 27.8 degrees Celsius, that's the equilibrium, minus my TI, which is 100 degrees Celsius, equals what? 0. Awesome. So now it's just an algebra problem. You solve for CS. Now I'll put it here, solve. So let's do this. So my suggestion, because I know this isn't a math course, but chemistry is a lot like math. Solve this first. Then put it to the other side, and then divide everything out. Okay? So do this first. I'll give you a minute before I do it to try it. Try putting it in your calculators, because the second most common mistake in this is not doing the algebra right. Okay? So take 1 minute and do this. time to do some algebra. So 100 times 4.184 times 27.8 minus 23.7. 1715.44. 1715.44 plus 59.047 grams times CS, 27.8 degrees Celsius minus 100 degrees Celsius equals 0. So I'm going to bring this to the other side as a negative and then divide everything out. So times minus 1, get a negative 1715. Okay, and then I can divide each piece out. Divided by 59.047, and then divided by 27.88 minus 100. And I get my specific heat of my metal to be 0.4028. So CS 0.403, I'll go with joules per gram times degrees Celsius. Questions? Did everybody get that tried it? Can I move on? I'm going to skip the next one even though I put it in here because I don't necessarily like the wording. I'll post the answer tonight. If we have time at the end, I'll go back to do it. I don't really like the wording. So we'll go to the next page. Everybody good with these coffee cup type problems? You put a metal in the thing or two solutions or whatever? MCAT? Remember, it's just MCAT. All right, let's keep going. For those of you that were in my sessions this week, I still didn't fix that. So there you go. That says something I'll decipher, but I still didn't fix that. I don't know what happened when I changed it to a PDF. It freaked out. All right. Let's start. This is bomb calorimetry. So, bomb calorimetry. What is the main difference between bomb calorimeter and coffee cup calorimeter? What? No mass. Cool. So what formula are we going to use? Awesome. When you see bomb calorimeter, think of Q equals cat. C delta T. Awesome. So the problem reads a 1 gram A 1 gram sample of octane C8H18 is burned in a bomb calorimeter containing 1,200 grams of water at an initial temperature of 25 degrees Celsius. After the reaction, the final temperature of the water is 33.20 degrees Celsius. The heat capacity of the calorimeter, also known as the calorimeter constant, is 837 joules per degree Celsius. The specific heat of water is 4.184 joules per degree Celsius. Calculate the molar heat of combustion. Keyword here is molar heat of combustion of octane. Okay? Molar heat of combustion. All right, so I'm going to do one of my amazing drawings again. So we have a tank. Here's my bomb calorimeter. Very crude bomb calorimeter nonetheless. Whatever. All right, there's my tank. The empty tank has a heat capacity of 837 joules per degree Celsius. Okay, the empty tank. We know we fill up the tank with 1,200 grams of water. Okay? So I need to find the heat capacity for the total thing. So in some problems, you won't have to do this. In some problems, it'll just provide you the calorimeter constant for it. I have another one, if you're curious. Number 2 is like that. We'll probably end up going over that. But number 2 is like that, where it just, you don't have to find the water, the heat capacity of the water. So I need to find the total heat capacity. And I know there are 1,200 grams of water in here. So what is the heat capacity? Heat capacity, not mass dependent, to change this 1,200 grams of water 1 degree Celsius. How do I figure it out? All right, so I know I have 1,200 grams of water. So there are, I'm not going to do it. All right, 4.184 joules per gram times degrees Celsius. Okay, grams cancel out, and I'm left in joules per degree Celsius, and I can add that together. So I get 1,200 times 4.184, and I get the heat capacity of the water is 5020.8 joules per degree Celsius. And I'm going to add that to the empty tank because remember, I have the heat capacity for the tank and I have the heat capacity for the water. And I need to find what it is what the energy requirement is to change the whole thing 1 degree Celsius. So I'm going to add this 837 joules, and I'm going to get 5857.8 joules per degree Celsius. So that's going to be my C, my heat capacity C, for my calorimeter. Questions on just getting the heat capacity C? All right, so I'm going to put that here. I'll put that here. 837 joules per degree. And equals 5857.8 joules per degree Celsius. Again, what's the difference between heat capacity and specific heat capacity? I heard it somewhere. Awesome. No mass. So this one's not mass dependent. This is the heat capacity for what we have here. Okay, you notice 4.184 is joules per gram times degree Celsius. This is just joules per degree Celsius. Okay? So now we're going to Q equals cat. So the molar heat of combustion. So after the reaction, the initial temperature is 25 degrees Celsius. The final temperature is 33.2 degrees Celsius. The heat capacity of the calorimeter, also known as the calorimeter constant, specific heat capacity, calculate the molar heat of combustion. Okay, so we're trying to find per every mole of C8H18, what is the energy? So we're going to go Q equals C 5857.8 joules per degree Celsius times my delta T, which is my TF, 33.20 degrees Celsius minus 25.00 degrees Celsius, which equals, on the calculator, we're going to get 48033.96 joules. Okay? So this is my Q for that reaction. All right. Back to the question. The question's looking for the molar heat of combustion. Okay? How much of the substance am I burning? One gram, given in the question, a 1 gram sample. Okay? It's looking for the heat of combustion per 1 mole of the substance. So now I have to figure out how many moles of the substance I have. Okay? Because we found the Q for the reaction, but we only burnt 1 gram. Okay? So if I burn, let's figure out what's the molar mass of CH18? Anybody? Awesome. 114 grams C8H18, 1 mole C8H18. So 1 divided by 114. What? That's fine. Awesome. Thank you. 0.0087 moles. It should be 8. I'll leave it as 88 moles of my C8H18. Okay? So I know that I have a very, very, very small amount. So do you expect when I burn a mole of it, do you expect the number to be a lot higher or a lot lower than this amount of energy? Molar heat. Lower? Why?
So this is the heat for the entire 1 gram sample.
Mm-hmm.
I'm just assuming a mole will be less than a gram.
Cool. Why is so we already found out that it's a lot less, and we know that 114. We're going to burn 114 grams in 1 mole. So do you think it'd be higher or lower than this one? What?
Not sure.
It's going to be a lot higher. So let's say I put a drop of gasoline on the table, and I light it on fire. We have a little thing going on. Now let me take a gallon of gasoline, and I pour it on the table. What's going to burn hotter or with more energy, that gallon of gasoline or that little drop? The larger amount. So we need to find it per that larger amount. And the units of the molar heat of combustion are going to be in joules per mole or kilojoules per mole or whatever we want to do. So we have joules on the top. We need to divide by our amount of moles, 0.0088 moles. And we're going to get our joules per mole. So it's 48033.96 divided by my answer, which is going to give us, I'm going to write it down here because it's a big number, 5475871.4 joules per mole. And that is going to be my molar heat of combustion. So for every 1 mole of gasoline, or in octane, which is a huge component in gasoline, for every mole of octane, how much energy is released? That number, right? 54.75. All right. We have number 2 here, which is a hydrazine problem, or a same type of problem. It's the exact same problem. So this says a 1.00 gram sample. So this is a separate word. This is a separate word. That's a separate word. That's a separate word. That's a separate word. And I don't know what happened here. All right. So it said a 1.00 gram sample of the rocket fuel hydrazine, given there, is burned in a bomb calorimeter. The temperature raises from there to there. the heat capacity calorimeter, including the water. It won't always say that. If it doesn't give you a mass of water, just assume it. Is 5860 joules per degree Celsius. Calculate the molar heat of combustion of hydrogen. All right, talk to the people around you. You have 3 minutes. 3 minutes. Should take no more than 3 minutes. Oh, missed it for a minute. Oh, man. How are we doing? Good. Good? Okay, cool. We doing okay over here? Yeah? Giving it a shot? Awesome. Doing okay? This gives me a chance to stand up and walk around. Because this is like hour 3 of reviews for me, so I've been sitting in the chair too long. How are we doing over here? Awesome, awesome. Yes.
So, I've got a question, because I always thought like a bomb calorimeter by nature didn't have water in it, which is why you didn't include the mass.
So what we do in a bomb calorimeter is usually it's given for Q for the calorimeter, okay? That includes whatever fluid they are in there, because we need something to absorb the heat of whatever we're doing. A lot of times it is water, okay? So a lot of time it is a tank with whatever, but it's already calibrated. That's what we say by the amount of water in there plus the tank is the calorimeter constant, which is our heat capacity of the calorimeter. So it's already calibrated in your question, okay? I just broke down the question a little bit more just in case you were to see it that way.
Okay.
Okay?
So in like a coffee cup, you're putting the substance in water.
Right.
Where in a bomb calorimeter, you're putting it in a closed chamber and the heat is...
Remember, it has to go through the metal and the water and then the tank. So it's the heat constant for all of that.
Okay.
Whereas a coffee cup, we're just worried about the water. Okay?
Thank you.
No problem. Questions? Good? Good? Doing okay? Yes? Awesome. Yes? For that one? Yeah, both. All right, that's a great question. Let me go over here. So that's, I turned it off. Oh, turn it on. That's a great question. So she asks if the joules per mole above should be negative. So we're looking for the molar heat combustion. So yes, the question phrased that way, it should be a negative answer, and I'm going to go up and change it to be a negative answer. Because remember, when we're burning something, can we relight the thing we're burning after? No, so by nature it's at a lower energy state, so it's giving off energy. It's an exothermic reaction. However, if your question's worded like it's asking for the magnitude, or like just how much heat is released or something, and they're all positive answers, don't freak out, okay? So yes, for molar heat of combustion, that should be a negative answer. All right, let's go ahead and go over this. So bomb calorimeter, what formula are we using? Awesome. Q equals C delta T. We have our delta T right here. We have a heat capacity of the calorimeter is that. Calculate the molar heat of combustion of hydrazine in kilojoules per mole. Okay? So we're going to go ahead and find our Q. C is 560 joules per degree Celsius times my delta T, which is 28.16 degrees Celsius minus 24.62 degrees Celsius. So we go 5860 times 28.16.62 is 20744.4. Awesome. So this is my Q given off in joules, or my Q. So I went ahead and swapped the sign right here because we're looking for the Q for the calorimeter or the Q for the reaction. Q for the reaction. So remember, the Q for the calorimeter, Q cal, or Q equals the negative Q of the reaction. Okay. That's, remember, going back to the coffee cup problem, Q for the calorimeter equals the negative Q of the reaction. So I went ahead and put a negative here so I don't forget it later. Okay? So I burned 1 gram of hydrazine. And I'm looking again for the molar heat of combustion in kilojoules per mole. So I burned 1.00 grams of N2H4. Okay. What's my molar mass of N2H4? 32 point what? 0486?
No, 046.
046. Grams, 1 mole, N2H4. One divided by 32.046 equals 0.30312 moles of N2H4. Cool? All right. So I'm going to ask the same question as last time. Do you expect when I burn 1 mole of this number to be higher or lower in terms of magnitude? Don't worry about the sign. Higher or lower than when I burn this amount? Lower? Higher? Lower? Maybe? So this is, I have 1 gram. Okay? I burnt 1 gram on the table. I have a little fire. Now I'm burning 32 grams, which is going to release more energy. The 32 grams or the 1 gram? 32 grams, cool. So I expect my number for my molar heat of combustion to be higher than this number in terms of magnitude, which means don't worry about the sign. Okay? All right, so we want it in kilojoules per mole. Let's get it in joules per mole first, and then we'll get it, well, let's just get it in kilojoules first. So in order to convert this to kilojoules, what has to be on the bottom? 1,000 joules to 1 kilojoule, which equals minus 20.744 kilojoules. Okay, and I want it kilojoules per mole, so I'm going to divide kilojoules by moles, and I'm going to get my kilojoules per mole. I get my negative 664.76 kilojoules per mole. Questions? Did we get the same answer? Yes, no, maybe? Did we get to this point? All right, can I move on? Is it okay if I'm going to turn the page? This is the same type of problem. This is just solving for a different variable. So I'm going to leave this one to you. Again, I'll post a solution to it. Go ahead and practice it. All right? I'm going to go to the next page. All right, Hess's law. All right, Hess's law problems. So again, this is the world's worst game assignment says. You're going to match this equation, and then match this equation. What did I just hit? We're going to match this equation with these reactions, and then add all the numbers. So it's a game of match and add. Okay? So, where is C2H4 in these reactions? Right here. Is it in the same proportion? Whereas what I mean by that is there's a 1 here, is there a 1 there? Awesome. And is it on the correct side of the reaction? Yeah, it's on the correct side of the reaction. So I'm just going to leave it alone. Okay? Where is H2 in these reactions? Right here. Is it on the correct side of the reaction? Is it in the same proportion in here as it is up there? So I'm going to leave it alone. Okay? Now I have C2H6. Where is this in the reactions? It's right here. Is it on the correct side of the reaction? I'm going to circle it. Is it in the correct proportion? Awesome. So what I'm going to go ahead and do is I'm going to flip the reaction. So in order to flip the reaction, what do I have to do? Awesome. I have to flip this sign. So I'm going to multiply this by -1. Okay? So that's going to give me my new reaction of 2CO2 plus 3H2O forms 3.5 O2 plus C2H6. I'm going to go ahead and cross that one out because we're no longer looking at that. This is our new reaction. Okay? And I have this over here. All right. So are all of the parts in this in the same proportions in these? Yes? All right. So let's go ahead and check. Let's make sure these cancel out. Everything else cancel out. So let's look at CO2. Where is CO2 in the rest of these? Right here, right? So 2CO2 is going to cancel across the equal sign. Things on the same side of the equal sign add up. Things across cancel out. So 2CO2 is going to cancel with 2CO2. Okay? Where's H2O? It's right here. It's right here and right here. Yeah, well, right here, and right here. So if you look on the left side of the equal sign, we have 3 of them because it's before the arrow. And on the right side, we have 1 here, and we have 2 here. So how many do we have on the right side? 3, so they cancel out. 3 cancels with 3. All right, now let's look at oxygens. On this side, we have 3 plus 1/2, and on the other side, we have 3 1/2. So these go ahead and cancel out. So what are we left with? We're left with C2H4, H2, and C2H6. So it becomes C2H4 plus H2 forms C2H6. Okay? And now we're going to go ahead and add these numbers together. Okay? Remember, we flipped the sign on this one. So we go negative 1, 4, 4, negative 1, what did I just do? Negative 1, 4, 1, 1, plus, because we just changed the sign, 1, 5, 6, 0, plus a negative 2, 8, 5.8. And we get delta H for this reaction minus 136.8 kilojoules. Any questions? I know Hess's law confuses some people. Are there any questions with this one? All right, let's go ahead and do this one. Yes, we had a question. Just looking, so this is your check. That's what we're looking for. This just proves you did it right. All right. I want you guys to try this one. This should take, I don't know, we're doing well on time. I'll give you guys 5 minutes on this one. So just so you know, we have 2 more Hess's law problems, and then some delta H formation / delta H reaction problems, and then we're done. So go ahead, give it a shot. I'll walk around. Take 5 minutes, 5 minutes. Yes. He's got a question first, then I'll come over.
I actually have a question about the earlier one you did, part 3, question 1 with this.
Mm-hmm.
Because I set it up as Q hot equals negative Q cold, and I got a different answer.
You really shouldn't.
Okay.
What do you mean? It's probably just a math
probably,
issue.
I just wanted to make sure, like,
No, it doesn't matter.
both of the formulas will work.
It's the same, because one, we're flipping the sign anyway, so it doesn't really matter.
Okay.
Because remember, one's going to be negative, one's going to be positive. It's both going to equal 0. Okay? No problem. All right, question.
So, when I was with you until you started doing all this. I understand that we're supposed to, the first step is we're supposed to more or less look for these and try to find them in these equations below. But none of these match up. So there's N4, which this is half of, there's 4 NOs, but there's only 2 right here.
So what can you multiply this equation by to make it
we're
equal?
supposed to balance them?
Just what do you multiply the whole equation by to match that?
Well, 2.
You multiply it by 2. You multiply the whole equation by 2. So you get 2 of these, 2 of those, and then you have 4 of that.
Yeah.
Okay? And then it matches there. And you do that. Negative 1 to flip, you can multiply by a coefficient.
Okay.
Okay? Give it a shot. Yeah, other question?
But how?
You multiply the number.
Oh, I got you. I got you. This was the change of H.
Yeah.
To find the change of
You multiply the 2 by the number as well.
Okay.
If you're doing that to a reaction, you're multiplying it by the number 2.
Okay.
Okay? No problem. Doing okay?
Yeah, I'm almost.
All right. Yes.
So, do you look for the leftovers of O2 since it's in multiple?
I always do O2 last.
Right, that's what I mean.
Yeah, you add them. If they're on the same side, you add it together. If it's across the equal sign, you cancel. So if O2 is on the same side,
Okay.
They'll add together, and then they should cancel out in...
Okay.
Actually, no, they're not going
But I flipped this one.
to...
So now O2 is on the product side,
Mm-hmm.
and O2 stays on the reaction side for this one.
Mm-hmm. So it can cancel out partially, too. So if you have 5 over here and 3 on this side, I'm not saying that's the case. If you have
Okay.
5 over here and 3 on this side,
Yeah.
you're going to do 5 here, so you're going to do 3 minus 5.
So
You're
it
going to
would
have
leave
2
on
left.
this side. But for this one, it would cancel out to be 1.
Okay? But it's in multiple places, right?
Yeah.
So I always save O2 to the last.
Okay.
Okay? So when you're manipulating the equations, if it's in multiple places, leave it till the end.
Okay.
Okay? Give it a shot. Doing okay? Yes. Doing good? 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 Yes? Awesome. All right, that's 5 minutes. Let's go ahead and go over these. Again, another game of Simon Says, match and add. So where's NH4? Or what am I doing? Where's NH4 in these? I mean NH4. NH3, where's NH? You know what I'm saying. Come on. Where's NH3 in these? It's in the second one. Is it on the correct side or the wrong side? The wrong side. And is it in the correct proportion or the wrong proportion? Wrong proportion. So what do I got to multiply this reaction by and the number by? -2. We're going to multiply. Whatever you do the reaction, you do the number. -2. So that's going to flip my reaction and multiply everything by 2. So we're going to get 4NH3 forms 6H2 plus 2N2. Okay? And then we're going to go ahead and cross this out just so we don't have to look at it anymore. All right? So there's my NH3. Is it in the correct side and the correct proportion now? Awesome. Okay, O2 is in multiple places. It's here, here, and it's here and here. Okay? So I'm going to save it to the end. If I have things in multiple equations that are in my matched equation, save it to the end and see if it cancels out. All right? Let's skip to NO. NO. All right, so where's NO in these? I just pointed to it. It's right here. Is it in the correct proportion or the wrong proportion? The wrong proportion, right? Is it on the correct side or the wrong side? It's on the correct side, so what do I have to multiply this equation by? Multiply it by 2, so what do I have to multiply this number by? What do I have to multiply the number by? 2, whatever you do the equation, you do the number. I'm going to put the new one down here. So we have 2N2 plus 2O2 forms 4NO as a gas. Keep the states. Don't get lazy and not write the states like I am. Keep the states because sometimes it'll have H2O as a gas and H2O as liquid, and that's a little tricky, but sometimes they do it and they don't cancel out. If it's in different states, it doesn't cancel out. Okay? So now I'm going to go ahead and cross this one out because I'm done with this one. Right? So we already did this one and that one. Where's H2O in this reaction? Right here, right? Is it in the correct proportion, or is it on the correct side or the wrong side? Correct side. Is it in the correct proportion or the wrong proportion? Wrong proportion. So what do I have to multiply this equation by? 3. So I get 6H2 plus 3O2 form 6H2O. I wasn't keeping track of where this is in the equation. This is in that equation, and these oxygens. Okay, let's see what goes ahead and cancels out. Okay, and I have to multiply the number by 3. All right, let's make sure everything cancels out except what we don't want to cancel out, and let's make sure everything's in the correct proportion. 6H2O, what does that cancel out with? 6H2O. I mean H2O. H2, you saw what I was pointing at. 6H2 cancels out with 6H2. 2N2 cancels out with 2N2. And let's take a look. We have 4NH3 plus how many O2s? Awesome, plus 5O2 forms 4NO as a gas plus 6H2O. Does that look like that? And we did our job. We can go ahead and add these up now. So, all right, we have 2 times negative 180.5 plus negative 2 times minus 91.8 plus 3 times negative 483.6. And we get a delta H for this reaction of negative 1628.2 kilojoules. Does everyone agree with my answer? Those who did it? I could have totally put something in my calculator wrong. Awesome. I want to make sure I didn't make a calculator mistake. All right, questions? This Hess's law problem. Okay. All right, there's one more Hess's law problem here. I'm going to leave that. So this is the last Hess's law problem I have for you guys. It's right here. I'm going to leave that to you, and I'm going to move to the next thing because we did 2 Hess's law already. You guys can practice this, or we'll do it at the end. Okay? I want to leave time for questions. All right. So I'm going to go ahead and flip the page. Delta H of formation slash delta H of reaction. This is going to be a pain with that chart. Man. Okay. So when you see, so the question is, find the delta H of reaction from the standard enthalpies of formation. All right. So when you have this type of problem, what should you be thinking? What's the formula we're using? Anybody? What's the formula we're going to use to find the delta H of reaction? Cool. So we're using products minus reactants. So we're using this. So this sigma. So we're going to use the sigma, which means sum, which means we're just adding something. Sum of products minus the sum of reactants. Okay, and that's going to equal delta H of reaction. All right, so we have standard enthalpies of formation, which are listed in like a table like this. One of these isn't listed. I forgot. One of these should be listed. I think it's carbon monoxide. Yeah, it's this one. That's my bad. We'll get there in a second. Sum of products, sum of reactants. So if I have 2, let's say 2 carbon monoxides here, what do I have to multiply the standard enthalpy of formation of carbon monoxide by? 2. Okay? So let's do this one first. So we're going to use products minus reactants. So I have my product of NaCl as a solid and H2O as a gas. So let's figure out their standard enthalpies of formation. So if I go down to the table, can I make this work? There, maybe. Okay. So we have NaCl as a product. Let's look for NaCl. NaCl as a solid is negative 411.0 kilojoules per mole. So minus 411.0 kilojoules per mole. And we know we have 1 mole, so it's just kilojoules. Okay? And we're going to add my standard enthalpy of formation of H2O as a gas. We have H2O as a gas right here, plus a negative 241.8 kilojoules. So there are my products. Now I'm going to subtract these from my reactants. So I have NaOH as a solid, okay, which is, you can't see that, right here, which is negative 426.7 kilojoules, plus my delta H of formation for HCl. HCl is, where's HCl? There, negative 92.3 kilojoules per mole. Now it's just a math problem. You just solve. So. So we get a delta H of reaction equal to negative 133.8 kilojoules. Did everyone get my answer? Yes. Where's this? What was it? H2O I'm looking for? Cool. All right. Yeah, H2O's here. You see, it's double rowed. Yes. That's a good question. How many moles are here? Are given in this reaction for, awesome. There's 1 mole of NaOH. So think about it like I'm multiplying by 1 mole. Okay? So if I do, so I'll put it up here. So if I'm multiplying 1 mole by something which is kilojoules per mole, what happens? Moles cancel and I'm left in kilojoules. So we have put an imaginary 1 here. If this were a 2, what would it be? What would this part be? It would be 2 times that. Okay? All right. Any questions? All right. I'm going to skip the next one because for whatever reason in the table, I think there was 1 more row that I cut off. Carbon monoxide is not in this table. It should be, but it's not. I think it's like 111, but I'm not even going to go there. Just don't worry about it. Okay? So what I want you guys to do is try number 3. I'll zoom out so you can see. Try number 3. This should not take more than 2 minutes. Go for it. go ahead and go over this. So products minus reactants, same deal. Sum of products, sum of reactants. So what is the delta H value, or H of formation for CO2 as a gas? Awesome. Negative 393.5 kilojoules. Okay. That's a good question. So we'll get there. Let's do the products first, and then we'll get to reactants. All right. So first product, we did CO2. Second product is, how many H2Os do we have? We have 2 of them multiplied by their H of formation. What's H of formation for H2O as a liquid? See, negative 2, 85.8 kilojoules. Okay, minus my reactants. So let's go with CH4 first. How many CH4s do I have? 1 of them. And what is my delta H formation for CH4? Minus 74.8 kilojoules. And let's take a look at oxygen. How does oxygen occur naturally? Awesome. So do we have to do anything for it to form O2? So there's no H of formation. For something that's elemental, how it occurs in nature, there is no H of formation. Okay? It's plus 0. So that's 393, 5. Minus 2 times. I get minus 890.3. Does everyone agree? Yes? Did other people get the same thing? Just want to make sure. All right. So right now we're at 5:05. We have these surveys. I'm going to go ahead and pass out, and now I'm going to answer any questions you might have for the test on old stuff, whatever. I really appreciate if you guys fill one of these out for me, and then just put it on the front table at the end. Just take one of these, pass it sideways. Take one of these, pass it sideways and back. Thank you. Yes. Q equals MCAT, the MCAT one, the Q equals CAT one, the work one, and delta E.
Okay, that's it?
And products, that one, products, reactants. They're coming back. Just you can grab one. Yes.
So for this exam, is it going to be like the last one where we're going to have like a question where he'll be like, during the combustion of like octane or whatever, and then we have to write our own chemical equation and everything. We're going to have to do that on this one, so we'll need to have memorized like the basic,
So
octane, all that stuff.
you won't have to know